Hello everyone, my name is Abraham Padriga, and for today's lesson we will be proving the inscribed angle theorem. For today's agenda, we will first do a recap of the inscribed angle theorem, then we will talk about the three different cases, and for the lesson we will be proving case 1 together, and then you'll be proving cases 2 and 3 with your peers through a think pair square. So previously, at the end of our lesson, we defined the inscribed angle theorem. Using GeoGebra, we showed that the measure of the inscribed angle of a circle is half the measure of its intersected arc. We know that the measure of an arc is equal to the measure of the central angle. And in both examples, the measure of angle BAC, which is also the measure of arc BD, is twice the measure of angle D. So this implies that the measure of angle D is 1/2 the measure of arc BC. And also recall that we can draw an inscribed angle when two chords have a common point. So an inscribed angle can be constructed in 3 ways, or 3 cases. So here are the 3 different cases. In case 1, we can draw an inscribed angle using a chord and a diameter. In case 2, we can inscribe the angle using 2 chords with the center inside the 2 chords. And in case 3, we also have the same 2 chords, but this time the center is outside. So today's goal is to prove the 3 cases of the inscribed angle theorem. And let's do case 1 together. A chord and a diameter forming the inscribed angle. So we'll name our circle A with center A and the points C, B, and D on the circle. So we get the given circle A with diameter CB and chord CD. And we want to show that the measure of angle BCD is 1/2 the measure of arc BD. So we will prove this using a 2-column proof. So the first step is to draw AD to form angle DAB and triangle ACD. We notice by the segment postulate. Having drawn AD, we know that triangle ACD is an isosceles since AC is congruent to AD because they are radii of the circle. The measure of angle ACD is equal to the measure of angle ADC, since these are base angles of our isosceles triangle. The measure of arc DB is equal to the measure of angle DAB, since we already established that the measure of an arc is the measure of its central angle. The measure of angle ACD plus the measure of angle ADC will give us the measure of angle DAB by the exterior angle theorem. By substitution, we know that since ACD and ADC are the same angle or are equal angles, we can add them, giving us twice the measure of ACD is equal to the arc measure of DB. And what we essentially did was substitution. Since the measure of ACD is congruent to BCD, we can say that the measure of twice the measure of angle BCD is equal to the measure of arc DB. And therefore, by dividing both sides by 2, we get the measure of angle BCD is equal to half the measure of arc DB. All right, so that was the proof of case 1. So now we will do our team activity, which is a think pair square. So in case you forgot, right, here are the instructions for a think pair square activity. So in groups of 4, each group will pair up like so. So, name yourselves A, B, C, and D. And in the first 5 minutes, pair 1 will prove case 2, and pair 2 will prove case 3. And after 5 minutes, in part 2 of the activity, we will switch our pairs and share your findings. So now it's your turn. So again, case 2 is the center is inside the 2 chords forming the inscribed angle, and in case 3, the center of the circle is outside the 2 chords forming the inscribed angle. So here's a hint. We can actually use case 1 to prove the 2 cases. So go ahead and work with your partners, and I'll go around the classroom to All right, so we're going to use case 1 to prove our cases. So just go ahead and work with your partners, and I'll set up the timer. All right, so that's time. So let's go over the proof of case 2. So given circle A, we get, and given chord CD and CB, we want to prove that the measure of angle BCD is equal to 1/2 the measure of arc DB. Now, this is similar to case 1 in terms of what we have to prove, but our construction is slightly different. So the first thing that we did, so in my hint, what I actually did was draw the diameter CE and chords AB and AD, forming triangle ACD and triangle ACB. And we can do this using the segment postulate. So now, if you remember, we can use the phrase without loss of generalization. We can say that the measure of angle ECD is 1/2 the measure of arc DE, and the same thing for the measure of angle ECB is equal to 1/2 the measure of the measure of arc BE. And we've already proven this stuff using case 1. So now all we need to do is find the relationship between these 2 angles and these 2 arcs. So using the angle addition postulate, we know that the measure of angle ECD plus angle ECB is equal to the measure of angle BCD. And by substitution, we can see that 1/2 the measure of arc DE and 1/2 the measure of arc BE is equal to the measure of angle BCD. Then by the arc addition postulate, we can add our 2 arcs to form arc DB. So that's arc DE plus arc BE. By multiplying both sides by 1/2, we get the following equation, which is 1/2 arc DE plus 1/2 arc BE is equal to 1/2 arc DB. So the measure of angle BCD is equal to 1/2 the measure of arc DB by the transitive property. And that's the proof of case 2. Now, I saw some of you struggled with case 3, but it is actually very similar to case 2. So let's see how that goes. So again, we're given the circle A and two chords CD and CB, but this time the center is outside our inscribed angle. And again, we're proving the same thing, right? So I should have changed the letters, but you know, computers. So again, we're drawing our diameter CE and chords AB and AD, forming triangle ACD and ACB via the segment addition postulate. And without loss of generalization, we have the measure of angle ECD is equal to 1/2 the measure of arc DE, and the measure of arc ECB is equal to the 1/2 the measure of arc BE. And again, this is case 1, and you could really tell that this is the same as case 2, right? So we've started the same two statements as case 2. But the difference now is that we actually subtract our angles to get angle BCD, right? And you'll see that we're also subtracting the rest of our angles. And the same thing goes for our arc, which gives us the relationship that we want, which is that the measure of angle BCD is equal to the measure of arc DB via the transitive property. And that's it. Thank you for joining me in this lesson, and I'll see you next time.